So next is the energy conversion in the bucket of a Pelton turbine. Now the energy conversion or work done by a Pelton turbine on the bucket is found by the change in momentum of the jet. So you can say the energy conversion or work done by the jet, okay, of a Pelton turbine on the bucket is found by the change in momentum of the jet. So this concept we use to find out the energy conversion in the bucket. Now say we have this bucket like this, okay. So this part is the splitter. So jet is coming out from the nozzle and striking the splitter, say along this axis. So jet is coming out, okay. So jet is coming out with velocity Vi. So this distance represent the Vi, okay. So here jet strikes at the splitter in the horizontal direction, means in the direction parallel to the shaft. So here the angles alpha I equal to beta I equal to 0 at the inlet of the jet. Now further, this bucket also moves along the tangential direction. It is mounted on the mounted on the runner, and it moves along the tangential direction. So it has some tangential velocity also. So that is given by u equal to pi d n divided by 60. Okay. So if I mark that u on this inlet velocity, that is say up to here. So this is my u. Okay. So with this velocity, this bucket moves in the forward direction. So there is a relative velocity of jet also. So the remaining part of this velocity gives us VRI, that is the relative velocity at the inlet. So Vi, you can say the absolute velocity at the inlet, okay, and VRI is the relative velocity at the inlet. If I can write, Vi is absolute velocity of jet at inlet, okay, and VRI is the relative velocity of jet at inlet, and u is the tangential velocity, okay. So here jet is going or striking to the bucket with this relative velocity VRI. Now when jet strikes, it divided into two parts. One part of jet goes along this, another part goes along this, okay. So here when jet comes out, so this velocity is along the tangential direction at this outlet. So here the jet is coming out with the relative velocity. So I write it as VRO. So VRO is the relative velocity at the outlet. Okay. So this is the relative velocity. So if I add in this in the vector form, if I add in this u, that is the tangential velocity, I got the absolute velocity of jet at the outlet, that is VO. Okay. Now I mark this angle of VRO with horizontal. Now say this angle is beta O. So this angle is beta O. And call this angle as alpha O. Okay. And this velocity is U. Okay. Now this is the one case. I mark it as case B. Now I have two more cases when this angle alpha O is less than 90 degree or more than 90 degree. So that is depending on the value of U. If U is less or small, the value of alpha O is less than 90 degree. If U is high, the value of alpha O is greater than 90 degree. So depending upon the value of U, now I have two more types of velocity triangles or triangles at the outlet. So if I try to draw it, now this is VRO. Okay, and this is my direction of U. Now say U is up to here. So then this velocity is VO. If I draw a perpendicular, okay, so this is the perpendicular over here. So this angle is beta O and this angle is alpha O. So this is case A when angle alpha O is less than 90 degree. Okay. Similarly, depending upon the value of U, the alpha O is more than 90 degree. So if I try to draw that, this is VRO. Okay, so this is my U tangential velocity. Okay, this is VO and this is my perpendicular on the horizontal. So this angle is beta O and this angle is alpha O. Okay, so here again alpha O is more than 90 degree. Okay, so these are called the velocity triangle. This is the case C. These are the velocity triangles at outlet. Okay, so we have three shapes of outlet velocity triangles depending upon the value alpha O, or you can say depending upon the value of U. So alpha O less than 90 degree, equal to 90 degree, and more than 90 degree. Okay, now here we have two more velocity components. One is the whirl component, one is whirl component of velocity, that is called whirl velocity. Okay, and another one is flow velocity. Okay, so this absolute velocity, VO, having two components, one along vertical direction, that is this one. So I mark it as flow component VF. So flow component I marked by VF. Whirl component I mark by VW. So at outlet, I mark it as VFO. So VFO is the flow component of velocity at outlet. Okay. And its horizontal component is VWO. So VW stands for the whirl component and O is for the outlet. So whirl component at the outlet is VWO. So here in diagram B, so this is equal to VFO. So in this case, VWO is 0. Okay. Or in this case, this is your VO. So here we have VFO and this is my VWO. Okay. So you can see here in diagram C, VW has same direction as VI. Okay. Or here VWO has opposite direction to VI. Similarly, if I see the whirl components at the inlet, so at the inlet, my VI is there. So this is horizontal. So that means VFI equal to 0 over here. Okay. And its horizontal component is whirl component. So that is equal to VWI. So VI is equal to VWI at the inlet. Okay. So this completes my velocity triangle at the inlet. So in case of Pelton turbine at the inlet, we have not the velocity triangle, but that is in the form of a straight line. Okay, so at the inlet, VI is equal to VWI. So you can say VWI in diagram A, VWI and VWO both have opposite direction. Okay, in diagram C, VWI and VWO both have same direction. In A, it is opposite direction, and in C, both have in same direction. Okay, so now I write some relations. So if I try to write the absolute velocity and the relative velocity, first we write the relative velocity VRI at the inlet. So I write VRI. So VRI at the inlet is equal to VI minus U. So you can write it as VI minus U, or also you can write at inlet VI is equal to VWI. So we have these two relations for inlet. Okay. So at the outlet, depending on alpha O or depending upon the value of U, we have three different velocity triangles. Okay. So this is A is for slow speed, B is for medium speed, and C is for fast speed or high speed. Okay. So now I write the force, the formula for force on the runner per unit mass. This is the per unit mass striking on the bucket. So that force I write as, so that is the change in momentum. So per unit mass, so our bucket moves along the tangential direction. So I take this force along the tangential direction. So that is the horizontal one. So this I write as VWI plus minus VWO. So per unit mass is there. Okay. So positive sign I use in A. So in A, okay, I use positive sign, and in B, I use, sorry, in C, not in B. So in C, I use negative sign. So now take diagram A for further calculations. Okay. So this is the force on the runner. Then I write the work done per second per unit mass. So that is the force multiplied by the distance moved in a unit time. So that is the tangential velocity. So this I write as VWI plus minus VWO into U. Okay. So this is the work done per second, or I can say it also, or energy transfer per unit mass. That is VWI plus minus VWO into U. Okay, this is the energy transfer within the runner. Okay, so I can also write the kinetic energy of jet per unit mass. So jet is striking with velocity Vi to the bucket. So I write this as 1 by 2 Vi square. Now this is my supplied kinetic energy. Okay, this is the supplied kinetic energy to the bucket. Okay, so now I write one efficiency. Therefore, I can write the hydraulic efficiency here, hydraulic efficiency of the turbine, that is eta H equal to VWI plus minus VWO into U, that is the energy transfer per unit mass in the runner, divided by the energy supplied, half Vi square. Okay, so this is the formula for hydraulic efficiency of the Pelton turbine. Okay, now I can write this hydraulic efficiency into another form also. So for figure A, you can see this is the figure A. So for this figure, I can write, so for inlet, I can write Vi equal to VO, Vi equal to VWI. Okay, so I can write at inlet VWI is equal to Vi, and at the outlet corresponding to figure A, I can write VWO. So VWO you can see here. Okay, so VWO, this is equal to the total part. If I mark it as green 9, so this total part, okay, minus U. So I write this total part as the horizontal component of VRO. So I write it as VRWO. Okay, this is the whirl component of relative velocity at outlet. So I can write VWO as VRWO minus U. Okay. Now further I can write VRWO. This is equal to, so I have this right angle triangle. Okay. So I can write VRWO is equal to VRO cos of beta O. So I can write VRWO as VRO cos of beta O. So therefore I can write again VWO as VRO cos of beta O minus U. Okay. Now let us say the relative velocity at the outlet. So that is VRO. The relative velocity at the outlet to be k times the relative velocity at inlet. So here I introduce a factor k. So this k is always less than 1. Okay, if I consider the friction of bucket surface. Okay, so VRO, here you can see this VRO. Okay, this is always less than VRI. If we consider the bucket friction, if we neglect this bucket friction, VRI is equal to VRO. Okay, so if I consider the bucket friction, so VRO is equal to K times VRI. So I again write VWO, that is K times VRI cos beta O minus U. Okay. Now further I can write K. Now VRI, you can see from inlet VRI. Okay. Now this VRI is VWI minus U. The total minus U up to here. So that is my VRI. So VRI I can write as VWI minus U cos of beta O minus U. Okay. Now further VWI is equal to VI. You can see here. So I write it as K times VI minus U cos of beta O minus U. Now I have the formula for hydraulic efficiency, this one. Okay. So I put here the value of VWI as VI. Okay. And VWO as K times VI minus U cos beta O minus U. Okay. So I can write hydraulic efficiency again. That is equal to 2 into VI plus K VI minus U cos beta O minus U into U divided by VI square. So I rearrange the terms and write the formula for hydraulic efficiency again. 2 times VI minus U into 1 plus K cos beta O into U upon VI square. So if I consider the bucket friction, I have this formula for hydraulic efficiency. So next I see the condition for maximum efficiency. So to find out the condition for maximum efficiency, I have to differentiate eta h with respect to u and equate to 0. Okay. So now I write d by du of this hydraulic efficiency to Vi minus u into 1 plus k cos beta O into u divided by Vi square, okay, and equated to 0. Equated to 0. So this term is product of two terms, okay, Vi minus u, and another term is 1 plus k cos beta O. So here, if I take constant terms out, okay, so I take it as 1 plus k cos beta O into u in, divided by Vi square, okay, into the derivative of, okay, I take the product uvi, okay, and minus u square, okay. So I take this u and this bracket equal to 0. So either this term is 0 or this term is 0. So this can't be 0. So I equate to 0 for this term, okay. So when I differentiate this, I got vi. So differentiate with respect to u. So I take it as vi minus 2 times u is equal to 0. So further, this comes out to be vi is equal to 2 times u. So the condition for maximum efficiency of a Pelton turbine says the inlet velocity of jet must be equal to 2 times the tangential velocity. Okay, so this is the condition for maximum efficiency. Okay, that is maximum hydraulic efficiency. Okay, now you can see from here, uh, so Vi, that is my uh, velocity of jet coming out from the nozzle. Now its maximum value is, or its theoretical value you can say is under root of 2gh. Okay, now this is equal to 2 times, now u I can write as ku under root of 2gh in terms of speed ratio. Okay, now here from this condition you can see my ku is 0.5. So this also proves that the value of speed ratio for the condition of maximum efficiency is 0.5. Okay. Now, however, if I consider here the value of CV, in that case, this value of Ku is less than 0.5. Okay. And that range is 0.46 to 0.48 if I consider the value of CV. Okay. Now, in all this derivation, I have put one assumption. You can see I have make here that my inlet and outlet is at the same radial distance from the center of the shaft or center of the runner. Okay, inlet and outlet is at the same radial distance. So for that purpose, now my this section of my bucket is horizontal. This section of bucket is horizontal. Only then I can put this assumption that ui is equal to uo, that is equal to u, which I use in further these equations. Okay. Okay. So this is my condition of maximum efficiency. Now you can also find out the maximum value of hydraulic efficiency, the formula for that. Okay. So for that I put u in this equation, u as vi by 2. Okay. So I write hydraulic efficiency again. So for maximum it becomes vi minus vi by 2 into 1 plus k cos beta o vi divided by 2 divided by vi square. So now you rearrange the terms again, and the formula for maximum hydraulic efficiency is 1 plus k cos beta o divided by 2. Okay, so this is the formula for maximum hydraulic efficiency. Okay, so these formulas you can use for the calculation purpose in various numericals of Pelton turbine. So with this, I end this energy conversion part of Pelton turbine. Okay, thank you.